Go.
I'm interested in non-invasive blood analysis, and there's a couple of key reasons, but the primary one is that you're going to be able to get results faster if you can do it instantaneously versus having to take the results, ship them off to the lab, and get them back. And particularly the type of analysis I'm interested in is with absorption and transmittance, which is basically when you shine light through, how much light is absorbed and how much comes out. So this phenomenon is modeled by the Beer-Lambert law, which basically says that the amount of light that comes out is dependent on how thick the sample is, the concentration of the absorbent in the medium, and how much the absorbent can absorb. And so this concept has been used really frequently for blood analysis, actually. In fact, pulse oximetry is a field where that's basically all they do. And so what they do is they look at the change in intensity of light over the time of a pulse, and by that they can tell you your pulse and also your dissolved blood oxygenation. So Samsung's taken this idea and tried to apply it to hemoglobin and hematocrit measurements, which are two elements of a blood panel. Unfortunately, they had over 8% error, and there's 3 reasons why. The first is that they went through the index finger. Now remember, in the Beer-Lambert law, it says that the thicker a medium is, the less light you're going to get off the other side. The second is that they were looking outside the medical spectral window. What that means is that the range from 600 to 1,000 light, or basically nanometers, which is basically red and infrared, is the range where blood works best. The reason for this is because when you shine white light through your index finger, you see that all the light that comes out is red. Blood is red, so it acts as a natural filter, only letting red light through. What they're looking at is 569, which is basically lime green light. And if you look, we have this LED here, which I don't have right now, but when you shine through, you actually get almost no reading. The second reason the third reason is because they used a photodiode. So basically what a photodiode does is it looks at the light that comes out the other side and it puts a number to the intensity that comes out, but it doesn't tell you the wavelength at which this intensity occurs. So what we do is we replicate Samsung's experiment, but we alter 2 factors. The first is that we go through the thumb webbing instead of the index finger. What this does is this decreases the thickness of the medium, which means that we can get more transmission. The second thing we alter is we use a spectrometer instead of a photodiode. This gives us more specific readings because it tells you the intensity at a given wavelength. In particular, we had 4 results, but they can be best shown by looking at a clean diagram first. So what you see here is that at 569, you have this really nice high peak, and then you have this smaller peak at 875. Now you might wonder, where does this come from? That's not supposed to be in the LED, and you would be absolutely right. This LED has an artifact or a flaw, which means that Samsung's not actually getting the readings they were expecting. The implications of this in particular, when you look at the finger, is that everything to the left of 600 gets smushed down. So because everything to the left of 600 gets smushed down, the peak of 569 is actually about the same size as the artifact that occurs. The second implication of this is the edge of the medical spectral window. So we have this spike that occurs at 610, and it occurs here, here, and here, and also in our other sets of data, for example, here and here. Now you might think this is another artifact, right? It's a wavelength that you see in all of your data that's not from the LED where it's supposed to be. And that's an interesting idea, but what we actually think is happening is that it's the edge of the medical spectral window. So everything to the left of 600 gets smushed down, but this stays up because it's in the red window. So we think that this spike is actually the edge of this tail. And our final finding is that you actually get a less noisy reading. So those are the results that we have with regards to Samsung's experiment. But in the future, what we hope to do is take this idea of going through the thumb webbing and running with it. And so right now we're looking at fluorescent effects, and we're going to see if we can model them over the course of a pulse. And then we're going to use those findings to come back to hemoglobin and hematocrit and see if we can try to replicate Samsung's results.